Hi everyone, welcome back to Bandwidth Audio's Project 2845. It's been quite a while since our last post, and we've had people asking us, when's the amplifier going to be done? When can I order one? Not entirely sure when they'll be ready to order. We've been facing supply chain issues, as everyone else has, in getting some components for the 2845 amps, as well as just keeping our other Bandwidth Audio products going and fulfilling orders. But we have been making good progress on the project. We finally have custom magnetics designed and on the way, hopefully due in, I think mid-June sometime. And so we've got custom filter chokes, power transformers, and output transformers. And the output transformers will be really quite a special design. It's the biggest transformer we've ever designed. And actually, I think I'll show a model coming up of kind of the core size of that transformer and what it takes to make a 40-watt single-ended transformer. I'll also show some other components in this video and kind of where we're at there. And then we do have the full preamp and pretty much full schematics of the amplifier designed and pretty much ready to go and ready to implement once we have all our components that can do the industrial design. And so I'll also show in this video where we're at with the preamp and kind of its final performance, which is really exciting, and I think the amplifier is turning out really great, and we're excited to button this one up hopefully relatively quickly once we get some parts in. So we're over here at the bench, and I wanted to show some new tubes we got in. So these are a relatively new 845 from a company called Linlay. They're a Chinese manufactured 845 that look really nice and just have really nice build quality. And so I expect them to last a long time as well and hopefully sound great. We actually have or I guess when we started the project, we were looking at and evaluating I believe they're pronounced Shiguang Chinese 845 tubes. Not sure if, how many of those are where, but I believe there was a fire at the Shiguang factory, and I think it's still, at this point in time, up in the air whether or not they are going to come back and manufacture vacuum tubes again or move to something, some other electronic assemblies or something else other than vacuum tubes. So I have a pair of those Shiguang 845s. But with what happened with their factory and their lack of availability, I went and purchased these new Linlay 845s. And so I got a quad of them in, and I expect to run these in the 2845 amp. And since I have a pair of the Shiguangs, I can do a comparison down the road on how they perform. We also have a new curve tracer where I can actually curve trace these on the computer up to a full 1000 volts and test their performance over a majority of their like nominal operating range, which is really neat. And so I've tested these in this quad compared to the Shiguang 845s, and they test extremely well. They're much higher performing, much closer to like what the typical data sheet of an 845 would show, as well as being tightly matched across this entire quad. So that's really encouraging. It really seems like, the Chinese tube manufacturers, or at least Linlay, has really listened to what consumers and what US manufacturers and customers have been expecting to get a higher, better performing tubes that are better matched. Really, it's the matching that we care about, especially with a parallel single-ended amp. The parallel tubes are both working together. You don't want one pulling a lot more current than the other, and overheating one and underworking the other. And so you really want them to work as a true pair, as if they're just one bigger, larger tube, rather than two independent vacuum tubes. And so anyway, the matching on these was really nice, and I was really pleased to see that. We also have in some new custom view meters. So let's see if I can get this to show up. These are from a US manufacturer where we specified a custom scale and our logo on these. And we've been really happy with how these work. We've developed a new driver circuit to drive these. And so these larger format, really high quality view meters will be on front and center on the 845 amps. And so it's, really nice to, again, have a US made, custom view meter from a company that's willing to tailor their products for a small audio company like us. So I'm really excited about these, and again, a really nice quality meter that's going to last a long time. Of course, these are also illuminated with a nice warm LED backlight. So, and not to go into too much detail, but it actually took some back and forth with just LED samples of us testing them and specifying the LEDs to put in here that provide a nice warm light that will illuminate the meter when the amplifiers are turned on. So, all this stuff, there's a lot more work that happens behind the scenes than what I'm showing here. So this is just a tidbit of kind of what's been going on. As I mentioned in the intro, we've been working on some custom magnetics. And so here's a power transformer from our Cascode 1 line preamp. And it's a pretty decent sized power transformer. And here's the core size. So the lamination stack size for the 845 output transformer. So this is what it takes to build basically a 40 watt single-ended output transformer that can do the full 40 watts down to 20 hertz. And so you can see the laminations, kind of the laminations on this guy. And that's kind of what we're showing here. That's the lamination stack on this output transformer. And so this obviously doesn't even have the thickness of the winding, which will be wound around the center somewhere here. So I'll make it even deeper once you add the winding. This has the bell covers covering the winding around the core. So you can see how large and how much magnetic material you need for a 40 watt single-ended transformer. And that's been actually a lot of the work we've been doing behind the scenes the past few months, is developing a better understanding of the transformers and how to estimate their performance to a much higher degree before we build them. A transformer like this is really expensive, so we want to get close the first time, especially when we get our first articles in from our manufacturer. And so with a core this big, the reason it's this big not only is to handle the power, but we also need the inductance to give us the low frequency performance. But with a core this large, the surface area, imagine winding copper around this, the surface area of the adjacent copper windings is huge. And so the potential capacitance between layers of the transformer could be really large and really hurt the high frequency performance. And so that's the magic, is how do you get a transformer that's this big to have really good low frequency performance as well as have great high frequency performance out to 30, 40, 50 kilohertz in a single-ended amplifier. And so that's what we've been spending a ton of time on. And that's kind of been, a lot of our development and R&D around transformers has been around kind of that problem. One of the other tools we have actually now to measure transformers is this inductance bridge. And so this is a general radio inductance bridge, which is designed for measuring inductors and does a really good job of measuring iron core inductors or transformers. And the way this works is you connect, the primary coil of your transformer or just the single coil of your inductor to this unknown terminal here. So your transformer is the unknown at which you're trying to find the inductance of. And the way this works is you basically tune the bridge such that you match the inductive reactance across the unknown terminals to a reference impedance that's built into this box. And so that reference impedance is actually calibrated and NIST traceable, so that such that what you're comparing this measurement or your unknown inductance to is a very well-known absolute impedance. So today, with modern electronics, you can measure the inductance of a load directly just by measuring, voltage, current, and maybe phase waveforms of what's happening at the unknown. But in this older piece of equipment, instead of that, we basically compare what's happening at the unknown terminals to a reference that's built inside the box, and we're tuning the matching with all the knobs here. And so this is an old school way, but still a really nice way. And in fact, this measures inductors more accurately than some $100,000 impedance analyzers today, to just a really high degree, again, because we're making a comparison measurement back to a precision reference that's just built into this box. So pretty neat. We also have another piece of equipment here, which is another inductance bridge, but this is designed more for output transformers. And so this inductance bridge works in a very similar way, except that it's designed to be high power. And depending on the range here, we can operate this up to 200 milliamps RMS current. So that's 200 milliamps RMS as a combination of AC and or DC current, and up to 1250 volts across the primary of a transformer. And so with this box, we can actually measure the inductance of a transformer as if it's operating in a tube circuit. And that's really the key with transformers, because the inductance in and of itself is sort of an elusive term. The inductance of a transformer, especially ones when you get into the size required for big tube amplifiers, is highly variable based on the operating induction. And what I mean by that is the input stimulus causes the flux to flow in the core of the transformer, and the inductance is a function of the flux flowing. So your AC input stimulus, AC and DC, in the case of a single-ended transformer, we've got constant DC current flowing through the core, plus our superimposed AC current, which is the AC is what we end up coupling to the secondary to the speaker. That combination of AC and DC determine where the core is operating with respect to its hysteresis curve. And large iron core transformers have fairly decent sized hysteresis curves, which cause the inductance to vary a huge amount depending on the operating conditions. And so this tool is exactly designed for that. This is designed for measuring high voltage, basically tube amp transformers as if they're operating in a circuit under all different scenarios. And with a single-ended transformer, some of you may know that the transformer is actually gapped, leading to a change in the permeability of the core and a change in the operating flux density. And so that gap is one parameter that is often tuned, and we will likely tune once we get our first article transformers in, to optimize the inductive reactance or inductance of the transformer relative to the DC current flowing in it. And I guess the point is this tool allows us to do that so we can fine tune our transformer design once we get it in and lock it in. This bridge over here, just for a quick background, is really for small signal. So this does, 10, 20, maybe 50, I think up to 50 volts actually, AC input only, and is not designed to handle, large currents or superimposed DC. So this is kind of precision. This is kind of the bronze, and is able to check, again, inductors under high power scenarios. So where we last left off with our preamp analysis, we had the full preamp stage working, and we were exploring in the last video I posted a few months ago at this point, how to get a little bit more headroom now that we had the cathode follower, which ate, if you recall, the cathode follower eats a little bit of headroom from what was available from the preamp. And so the answer was really just moving to higher voltage. And what we ultimately moved on the preamp was to a 600 volt supply on the cathode follower stage and our 6AH4 stage. And so in doing so, we've also increased the cathode resistor on the 6AH4 stage to get even more bias voltage and therefore even more input headroom to the stage to get maximum signal swing out of this. And so that's why you can see here with the 1.8 k ohm cathode resistor on that 6AH4 there and 32 volts of bias, you can see how much headroom we have before the stage clips. It's been pushed way out past 200 volts peak. If you recall, the target, I believe, was 170 volts peak plus some margin. So we really wanted to get as close to 200 volts peak output swing of the full preamp to drive the grids of the 845s to maximum output power and with headroom. But what's interesting here is you can see by moving from 1.5K on that cathode resistor to 1.8K, we also get much better THD performance. And that's due to the local degeneration of the stage by basically developing an opposing current to the grid based on the conduction through this tube. And so I think I mentioned this before, but this is typical degeneration where you develop a basically current feedback through the stage because of the voltage drop from here to here for a given current flow. The grid obviously is coupled through ground, sees that voltage drop as feedback. But what's interesting is I was surprised at the improvement, even though we have, if you recall, constant current sources, which basically make the load line on this tube flat. So even with a relatively flat, or based on the impedance of this, basically a perfectly flat or horizontal load line on this tube, giving us essentially the amplification factor of this tube as its gain, it's interesting to see that, you know, the degeneration still matters. And that was actually a little bit of a surprise to me. But you can see how much better performance this has. So this is running with the 6AH4 as the second gain stage, and the parallel 6BX7 cathode follower as the to drive the grids. And so again, we've got tons of headroom, amazing THD performance for how much voltage swing this thing has, right? We're clipping right about at 1%, which for a single-ended amp is pretty unbelievable. So really, really great signal swing. And I guess if I move to some other tabs, we can see what the bandwidth looks like at different signal swings. So this is 100 volts RMS, 50 volts RMS, and 25 volts RMS at the output of the preamp. And we can see just how wide the bandwidth is. And the minus 3 dB point is beyond 100 kilohertz out here. So minus 3 dB is over here. So we're at like 125-ish kilohertz, or maybe even further, of bandwidth to minus 3 dB on the preamp. So this performs really well. I guess the last update with regards to the preamp is what I realized is two 6BX7s in parallel for our cathode follower, believe it or not, have the same performance as a triode strapped EL34. And so in the preamp chassis, one of the things I tried was just that. I removed the 6BX7 and triode strapped an EL34 as our cathode follower driver. And sure enough, we get nearly the exact same results and nearly the same headroom, because the gain, the transconductance, and even the operating curves align perfectly with a paralleled 6BX7. So I thought that was kind of neat. And I tried the EL34 and also got amazing performance. And in fact, for the design, my plan is to move forward, or at least the plan of record is to move forward using an EL34 in this stage. The reason being is, if you recall, we've got 30 milliamps of current flow set up by this constant current source through the cathode follower. And for a 6BX7, that makes the static power dissipation of the parallel 6BX7 a little bit high. For an EL34, which is a really high power tube, the DC power dissipation in the tube is much lower compared to its maximum ratings. And so an EL34 triode strapped will last a lot longer in the stage and maintain its robustness over a really long life, which means the amp will maintain its sound and its hopefully very robust bass and drive characteristics for a much longer time as the tubes age compared to like the 6BX7. And so that's something I can experiment actually once we build this amp, is I can try the EL34 or a parallel 6BX7 in the cathode follower stage and just see what I like more. But like I said, right now the plan is to move forward with this EL34. So here's going back to the curves, this is the same curves now. This is our headroom. We're looking at the headroom with the EL34. And so if I can get the camera to focus, there we go. We can see that the EL34 is this yellow curve here. The 6AH4 plus 6BX7 cathode follower at 600 volts is blue here. So a little bit of reduction in THD, but that's honestly most likely just general tube variation more than anything else. And then the previous 500 volt curve where we had the lower cathode resistor and less headroom is that orange curve here. So basically our two options are, we're operating in this region now, and we can run either the 6BX7 cathode follower or the EL34 cathode follower. If I scroll down, this is just now viewing the output power on a linear scale rather than a log scale. You can see how much headroom we have. And so with the EL34 in yellow, we start to kind of taper up towards clipping at around a 206 volts peak. So it's 412 volts peak to peak, more than enough signal swing for our 845 grids with lots of headroom to spare. With regards to bandwidth, again, the EL34 performs really, really well, no issues there. And in fact, has a little bit better low frequency performance compared to the 6BX7, which may be a function of its plate resistance. I think maybe its plate resistance is a little bit lower than the parallel 6BX7, so it's able to drive some low frequency loads maybe a little bit better. But in general, the performance is great. Bandwidth is super flat, as well as the THD. So here's the THD versus frequency for various output levels, and look how flat it is. This is why open loop amps are amazing, right? Feedback amplifiers at the frequency extremes try to compensate for the amplifier's roll off and drive the input harder. That's what makes feedback flatten frequency response. But in doing so, because you're driving the preamp harder at the frequency extremes of the amplifier and feedback, it tends to make the THD curl up at the bandwidth extremes. And so this amp remains really flat in THD all the way out to 80, 90, 80 or 90 so kilohertz. It starts to taper up a little bit here. But keep in mind, we're at 100 volts RMS signal swing, which is, I believe, very close to the 170. Yeah, a little bit shy, but very close to the 170 peak. These numbers are RMS. And remember, we needed 170 volts peak output for maximum output power. So regardless, though, look how flat the THD is. This rise at high frequency is caused by the impedance of our constant current source rolling off and basically not presenting either the cathode follower or the 6H4 gain stage. They're not providing the tubes with as high of impedance at higher frequencies because the capacitances between the nodes and the MOSFET depletion mode MOSFET characteristics and capacitances cause the impedance of this guy to roll off. If you recall, we did some analysis in a few videos back on benchmarking what the impedance is of these constant current sources, and these are well over 10 mega ohms, I believe, in most operating conditions. But at some point, their impedance starts to roll off, in which case the load line on the vacuum tube starts rotating from perfectly horizontal. It starts rotating a little vertically, which means we get a little bit of reduction in gain, which is causing partially the bandwidth to roll off at high frequency, as well as increasing just the general harmonic distortion of the stage. It's approximating closer and closer to having a smaller resistor value on the plate of the tube at higher and higher frequencies. And so that's causing this roll off here. But again, this is way outside the audio band. And for a single-ended amp, our transformer bandwidth is probably going to start rolling off here anyway. And we're, we're not quite, but we're getting close to an order of magnitude above here, the audible range. So this is really just a non-issue, and I think will be lessened. This extreme will be lessened, but once the amp is complete, just because of the bandwidth of the output transformer. So anyway, that's where we're at with the design. Extremely happy with it. As I mentioned in the beginning of this video, we have essentially full schematics, including the power amplifier design, the power supply, which is a beast. We've got a lot of the power supply circuits designed. And so really we're just waiting on components and getting pieces in to start building the first the first unit, and we'll kind of build up one chassis and test it as we go. But I'm really excited for this. This should be one killer audio amplifier and just sound unbelievable while still be able, drive a wide range of speakers with kind of the classic single-ended triode sound with really none of the drawbacks. Maybe except for weight and power dissipation. This is no small amplifier. So I hope you enjoyed today's video, and take care everyone. Thanks for watching.